Hey everyone, welcome to another deep dive video with me and Erik. This week we're looking at the Sieve exercise. This is a really interesting exercise. It's a really old algorithm. It's like a 2,000-year-old algorithm that we're now looking at how to implement in modern programming languages. We're going to be looking at a few different solutions, a few different approaches. We're going to start off with one type of solution, which is around looping and keeping arrays, another one that uses sets. We're going to end up looking at some recursion in F#. So there's all sorts of interesting stuff to see. We're also going to touch a bit more on concurrency after the last video that we did on concurrency and parallelism, which if you haven't watched, I do recommend going and looking at. I hope you're enjoying these videos so far. Thank you to everyone that's been putting comments in the bottom and telling us which of the solutions they're enjoying, sharing their own solutions. That's a real boost to both me and Erik. So if you do enjoy the video, please do leave a comment. Please do tell us which solutions you're enjoying. Tell us what you'd like to see more of, and we'll try and make sure that we tailor these videos moving forward. So Erik, we're going to start off with you telling us a little bit about what this algorithm is. As I said, it's about 2,000 years old, really classic algorithm. Take it away.
Yeah, so the algorithm is an algorithm to find the primes up until a certain number. So if you pass in 10, it will give you all the primes up until that number. And how do you do that efficiently? There are lots of different ways, but the Greek mathematician Eratosthenes came up with the Sieve algorithm, which became the Sieve of Eratosthenes. That was in the 3rd century BC, so that's almost 2,300 years ago. And the algorithm is such that you cross off multiples of your prime, because a multiple is by definition not a prime. So suppose we were to find the primes up until the number 10. So what you would do is you would get a piece of paper, and you would put all the numbers on the paper. So you start with 2, of course, because that's the smallest prime. So you have 2, 3, up until 10. So you start with the first number, it's 2. It hasn't been crossed off because, well, we haven't done anything yet. And any number that isn't crossed off on our sheet of paper is a prime. So we're marking 2 as a prime. So, but what we then do, that's the key part of the algorithm, is we're going to cross off all the multiples of our prime. So for 2, that is 4, 6, 8, 10. So we're crossing them off in our list. Then we're done, and we're moving on to the next number in our sheet, which is in this case 3. Well, 3 hasn't been crossed off, which means it is a prime. And then we're going to do the same thing again. So we're crossing off the multiples of 3s, which in this case are 6 and 9. So 6 was already crossed off, so we could skip that, but we're crossing off all the multiples. Then we move on to the next number, which is 4, but that is crossed off. So we're going to skip that because it was crossed off, and that means it isn't a prime. So then we get 5, which isn't crossed off. We found another prime, crossing off all the multiples, which is just 10 in this case, etc., until we reach the end. And then at the end, we can just find all the primes by looking what is not crossed off. So that will be 2, 3, 5, and 7 in this case. And that's an efficient, it's at least a straightforward way to find primes. Whether or not it's the most efficient, it isn't, but it's probably very easy. It's one of the easiest algorithms to generate a prime that I've come across when doing a little bit of research.
Nice. Okay, so we're going to look at how we do this in code. Our first solution is this one here in C++. You'll see on a few of these that it's Erik's solution in C++. Erik, I know you've actually sort of just taken other people's solutions and reformatted them a little bit so we can have them showing up nicely on these videos. Talk us through this. This is sort of the canonical solution that we're going to be using, really variants of this throughout the rest of the video. So we'll go into a bit of depth on this one just to make sure everyone's clear on it.
Yeah, because, well, this is a very fixed algorithm, so most of the solution will follow the algorithm, because so they will be similar, but there will still be differences and interesting ones at that too. So the key thing here is a function prime with a maximum value, but on line 8 is where we define like our sheet of paper. We're calling it Sieve here, which is an excellent name. So it has max plus 1 values because, well, a vector is 0 indexed, so we have a 0th element, and we don't want that. So we do max plus 1, and we're initially setting all the values to true. So that's the second parameter. And this means like basically it's not crossed off. It's a prime. So when we start out, we just assume everything's a prime. But we're going to cross off things later. Then on line 9, we get a second vector, and that vector is of integers, and these will be the actual prime numbers. So just to go back a little bit, that sieve is a vector of booleans. So just true or false values, which is basically, is it a prime or isn't it a prime? Or in the terminology of the sieve, is it crossed off or isn't it crossed off? And then we get to a loop. So we're starting with 2, which is the smallest prime, and then we're looping up until the maximum value and incrementing I by 1 each time. Then the first thing that we do within the loop is we're going to check, is this a number that is already crossed off? So we do that via indexing. We're saying sieve and then the square brackets I, which means at the ith position, is that a false value? And if it is a false value, it's not a prime. So we're going to skip it. If it is a prime, then we can continue and we can add it to the primes list. So that's what the pushback does. It adds it to the end of the vector. So the I is the prime. And then we're having a nested loop. And that nested loop starts at I times 2. So that's the first multiple of the prime. And then it will keep on looping up until it's at the max value. But the thing is that we are incrementing that the j value, so that inner loop value, by the prime, which is I in this case. So that's what you're now highlighting, so that we get all the multiples. So this will be 4, 6, 8, 10. And then for each of those values, we're setting the value to false in the sieve. And then we're going to do that for the next number, etc., until we reach the end. And then the primes vector will hold all our primes that we found.
Nice. And then we return that at the end. Nice and simple.
Yeah.
Okay, so that's a straightforward way of doing this. So we're going to move on and look at a C# version of this. Again, one of yours. We'll skip that at the top. This is very similar. This is actually one of yours.
Yeah.
So this is very similar again. The same algorithm basically.
Yeah.
But the difference is this really, Erik. This use of this BitArray.
Yeah. So why did I change it to a BitArray? We had a vector of booleans, which sort of makes sense. Either it's a prime or isn't. So a boolean is enough information. But it gets at one of the problems of the sieve algorithm, is that it is quite memory intensive. So I mentioned getting the numbers up until 10, which is of course a smallish number. So we're going to get a vector of 10 booleans, 11 actually in the C++ version. But a boolean, a boolean is true or false, so it could be a bit, so on or off. But in most of the languages, a boolean is stored as a byte. So that means for a single true or false value, it will be 8 bits and 1 byte of information. So for just checking up until the value of 10, we need 11 bytes. So it's quite wasteful, actually. So is there a better way that we can do this? Well, yes. We could sort of map this onto bits. So we could, for example, take, if we're going to get, let's do 1 byte. So with 1 byte, we get 8 different bits. And we can say that the 0th bit is the flag for the number 0. The 1st bit is the flag for the number 1. And the second, etc., etc. So basically what the bit array does, it encapsulates a bit of Boolean, of a bitwise magic for us, where it looks like we're just dealing with a vector of Booleans, because this code is almost identical to the C++ version. But under the hood, what it will do is it will not store a vector of Booleans, but it will use integers and then use the individual bits in the integers for each of the indexes. This means that, so as I mentioned before, so we can get 8 numbers of information in a single byte instead of having to use 8 bytes for them. So this is roughly about 8 times more memory, uses 8 times less memory for the sieve. And of course, it depends on your language, and some language might even optimize things. But roughly speaking, this is a lot more efficient. And there are actually also more ways in which you can modify the Sieve of Eratosthenes to be more efficient, and that's to partition things. So you're calculating the sieve of a small block first, and then you do the rest later on based on what you already have. We're not going to go into that because basically nobody ever did that as far as I could find. But if you are interested in that, you check out Wikipedia. That has a nice section on that. So for this solution, just remember that we're using BitArray to optimize for memory.
We talked about this before. We always just have a little look through the solutions before we start recording. And Erik was telling me this, and I was like, no, surely a boolean's just, surely a boolean is a bit. And Erik corrected me, as Erik often does. And it really surprised me that, every time we're storing a boolean in any of our programs, we're using, 8 bits of memory for that when we don't need to. This is a general optimization that I guess you could use in lots and lots of places. It's not just in some algorithmic thing like this, but if you are storing large amounts of or holding large amounts of booleans in memory at the same time, this is a really interesting approach. The other thing I notice here, Erik, is before in the C++ one, we had these 2 different vectors that we were using, whereas in C#, we're only storing 1 array in this case. But I also noticed that we are yield returning on each iteration of the loop, which is obviously a slightly different approach. Do you want to explain what yield return means in C# for everyone?
Yeah, so this is basically a lazy sequence. So this has to do with concurrency and the ability of execution of a bit of code to pause and to continue later on. So what this will do is the caller will get back a lazy sequence. This is in C#, it's an immutable of integers. And that could actually be an array under the hood, but in this case, it's not. It's a lazy sequence. And it means that it won't actually really do anything unless you ask it for, give me a concrete value. So for example, if you want to get if you call primes and then you say, give me the first 5 values, then of course things must be concrete and the actual values have to be computed. But if you just call the function, nothing will be done, really. You just have a reference to a thing that can give you primes. So you can say it was sort of started, but it is in a paused state. If I were to ask it for the first item, then it will give me the first item. So that's that yield thingy. So the way that you could envision this, it would run all the code up until the yield. It will give me the value back, and then it would pause. It would say, hey, I am done with giving you that single value that you need. You decide what you want to do now. So you could do something else. But if you then decide, hey, I also want to get the second element, then the thing that was being paused will run again up until the next yield return. So it will give you these values lazily, and that is one of the great benefits of this is that it could be beneficial for memory because we don't have to store all those primes in memory. We just have to return a single one of them. That is technically.
But would it actually? I was going to say, would it actually be efficient though? Because you say it's pausing things. It's still having to keep this in memory, waiting for the next iteration to come through. And this is actually a much larger data structure than the actual list of primes. I mean, maybe slightly less because it's a bit array, but certainly going back to the C++ one, this has got a lot more data in it than this has. But in this lazy evaluation, it's this one that we have to keep around. Whereas in a normal evaluation, we get to return the whole of this smaller list out of it.
But you're now, but in the C++ version, you're having 2 bits of data that you have to store. And we only have 1 bit of data here that we store. The downside is that the whole being able to pause and to continue, that also costs a bit of memory. So there is a bit of It's not that this is always better for you. It completely depends, but
yeah,
it could be.
yeah. So I guess it's going to come down to what's happening within that loop, because you might be holding a whole load of information to be able to continue iterating.
Yeah.
And also whether there's a chance you may or may not break out early. So, if actually you're just looking for a value and you get that value you return, this is potentially massively efficient. But if you're going to iterate through the whole thing eventually, then actually this might not have a sort of performance benefit.
But then
again, it's really interesting.
It might, if the number is really, really big. So if you're storing like, I don't know, 1 million primes, you would get a million of those integers in memory. Whereas with this version, you would just return that single integer. You're probably still keeping it in memory because the caller has to do something with it.
Yeah.
But if it's just logging to the console, for example, it will be.
Yeah.
So it's trade-off.
You're keeping all of the bits in memory here for it.
Yeah. I must admit that I often just write this because it's less lines of code. It's just
it's really nice. It's functionally really nice, but I could imagine you could ignore the fact mentally that this whole thing is being kept in memory. Think, I'm not having to keep that extra array, and then be surprised with that massive memory payload that you've actually got there. But the fact that this is bits, not booleans, does make it potentially a lot more efficient as well. Because if you were going up to primes that are in the millions, then you're gonna have a huge. So there's definitely a trade-off to work out and solve in all this.
Measure.
Okay, cool. Yeah. Okay, let's look at Julia, which is the next solution. Erik, again, this is another one that's in the same sort of family of solutions.
Yeah, definitely.
Do you want to just talk us through this for anyone that's not familiar with Julia?
It's very much a sibling of the others. So the S is the sieve on line 2. So it says fill true limit. So that basically says we're creating a list or a vector, whatever you want to call it. So we're creating a collection of elements of limit size that are all true. So in this case, we're saying, hey, if something is true, it's a prime. So we did that before. Then we're saying the very first element, Julia starts at index 1, is false. So of course, 1 is not a prime. So basically, we're crossing 1 off. And then we have, instead of having the nested loop, we have a sort of different way of writing the nested loop. It's just some syntactic sugar. But you have n is 2 to the limit. So that's our regular for loop, our outer for loop. And then we have our inner loop, which is after the comma. So it's not really an inner loop because it's basically appended to the other condition. But you can see this as just being an inner loop. So it's doing the two things. So it's first doing n in the range 2 of limit. So the start of n is 2. And then it will do iterate through all the k values. So that starts off the 2 n's and then increment by n. So you can see that this range notation, where it says k is 2n colon n colon limit. So that's basically the same as 4j is 2n, and then j less than or equal to limit, j plus equals n. But in a very, very succinct way. And I always love ranges, and I think they make the code just a lot easier because you don't have all the shenanigans around it. But other than that, it's basically just the same. So the thing that is that they don't do here is to check whether or not it was already crossed off, because that's not really what this is about, because you don't need to do that. You can just cross all the multiples off because they wouldn't be primes anyway. And then at the end, you do find all. So what this does, it will give you all of the indexes where the value is still true. So that's finding our prime. So we don't sort of have to keep track of our primes ourselves. It's there's a function to iterate over this and efficiently. And this could actually be using a BitArray like thingy under the hood. I'm not entirely sure how Julia does it. I wouldn't be surprised that it does some really nifty things here because it's a very performance-oriented language. But the code is very, very small. It's smaller than our C++, and C# versions, and I quite like this.
Do you think this is more true to the original algorithm?
Yeah. I don't think the original algorithm has the keep track of all the primes in a separate thing. So it's just a sheet,
Yeah,
and then
exactly.
just look at everything that isn't crossed off. And I think this is probably the most direct translation of the algorithm that I've seen.
Mm-hmm. Yeah, I really like this. It's nice to see. I always like looking at languages I'm not familiar with, seeing some cool stuff they're doing, and just sort of understanding how readable that language is. Because often you look at code that you're not familiar with, and it can feel a bit like not knowing whether what's hard is the code or this double loop thing here, or whether it's just not understanding the algorithm. So it's a nice example of it's actually very, very simple code once you understand the algorithm. So yeah, I like this one. Okay, let's move on. So this is R, another performance language designed for this sort of stuff. Talk us through this one, Erik. What are we seeing here?
Yeah, R is has a lot of things that it shares with Julia. So line 5 and 6 are just using different functions and a bit of different syntax. So we're creating something, our sieve, initially all of limit values, and at first they're true, except for the first R element. So R is also 1 based indexed. So it starts at 1, not at 0. But the thing that this implementation does differently is that it optimizes for runtime performance. So instead of doing 2 up until the limit, we can actually stop when we're at the square root of the limit. And it is guaranteed that any number above the square root of the limit will have been crossed off anyways by one of the previous numbers. So you don't have to worry about stopping at the square root of the limit, because any of the other values will have already been crossed off by other values. And we're saving a lot of stuff here. So I don't know if we had the limit of 25, we could stop at the square root, which is a lot less than what we were doing previously. You're saving a lot, and the bigger the number, the more you're saving. And then within the loop, there's a little extra check. Numbers I is checking if it is crossed, if it isn't crossed off, and then so it's a prime. But it also has to, if the I squared is less than the limit, that's a little thing that we need to do where you can just forget. It's just like we're saving ourselves from we're doing this for the next line. So without this will break, because then the sequence is not right. So you can sort of forget about that. But the key thing here is the sequence, that we're not starting at I times 2, but we're starting at I squared. So again, so for 5, we would be starting at 25 instead of at 10. So we're saving a lot of checks that we don't need to do. So basically there's less looping involved here. And it still all works because it's guaranteed. I don't have the mathematical proof here for you, but it will be out there somewhere. So it still works with all the tests. So you're just doing less work and still finding the same things, because anything that you were skipping over would have been covered in any of the previous prime numbers that you would have found anyways.
Right. So just to think this through, because this is a bit complicated for my poor non-mathematical brain. So if we were looking at 25, the square root of 25 is 5, right? So we're only iterating here from 2 to 5.
And crossing off all the multiples of them.
Yeah. So what we're saying there is if you've got a number, let's take 7. So 7 isn't covered in this range. So I will never be 7. But we're saying that the multiples of 7, which I guess are 14 and 21, will both have been crossed off by other things. So 14 will have been crossed off by 2 and 21 by 3. And so that's basically just some maths magic that makes this algorithm work. It's exactly not intuitive at all that would work to me. But
me neither.
Yeah. Okay.
That's why I'm not a mathematician.
Yeah, and then at the end we just no, exactly. And then at the end, this is just the equivalent of a find all again.
Yeah.
Okay, right. I mean, I would not have got that while you were talking. My brain was rattling away trying to prove that to myself in my head and failing. But that's really cool. That's a nice little cheaty shortcut then to make that work. Okay, nice. Let's keep moving. So this is Python, and this is the first one that I guess like deviates from the pattern that we've seen so far significantly.
Yeah, it's in the spirit of the sieve, but it's not creating a single sieve and then crossing off the multiples. But it is doing some nice things. So numbers are, well, basically that's our sieve, but instead of crossing off things from the sieve, we're creating a second set with all the multiples. So that's online. That's that whole 2 times n. So this is giving a new set that contains just all the multiples. So not the numbers themselves. So for our example of 10, it will be the multiples of 2. So it will be the multiples of 3, etc., etc. So in the end, that gives you a set. So only the unique values. And well, of course, the primes are all the numbers minus the multiples. So you can sort of see that numbers minus marked. That's sort of intuitive, like. Well, sets don't have ordering usually. You have things like ordered sets, but in most cases, sets are unordered. So that's why we need the sorted, because the tests expect the primes to be returned in their actual ascending order. So that's why you need sorted. Yeah. But this has the general idea of the sieve that you have numbers, and if you cross off any multiples, then you will get the primes. But it's not entirely the Sieve of Eratosthenes algorithm.
No, but that's cool. It won't be very efficient, I guess. This
I know, not really.
But, yeah, it's nice. It's always a little tricky, I think, looking at the list comprehensions in Python to immediately sort of grasp what's going on. But I guess it's looping through this first and then looping through this second.
Yeah.
So it's a sort of double loop thing that we saw in Julia a little bit.
So you have to,
Cool. Okay, and then just looking at a similar solution in Raku. Raku, if you're not familiar, is Perl 6, but they diverged so much from Perl 5. They renamed Perl 6 to be Raku, and it's its own language now. But this does look a little like Perl, Erik. We've got dollar signs and underscores and dots and all of the fun stuff that we've got something here. I have no idea what this is. All of the fun stuff that you expect to see in Perl. So go gently on us as you talk us through this one.
We got maths again. So hooray for us.
Again as
well, I'll start with the simplest bit, which is the last bit of the line. I have 3. So we have 2 ... $n, and dot is usually a range. In this case, it's a range. So we're creating a list of all the numbers 2 up until n. So that's our sieve. So far, so good. Then the second thing that is happening is that whole map thingy. So the thing between the curly braces is code that is applied to all of the numbers in that range. So it will start applying this to 2. And so $_, that is the number itself. Then you have 2 times $_. So that's so it might be 4 if we have if the number is 2 up until the end. So this will create basically it will map a number to a new list of the number and all its multiples. So if you start out with 2, you get the 2, 4, 6, 8, 10. If we stop at 10, and then the second number in that range was 3, so you get 3, 6, 9. 4 is 4 and 8. 5 is just 5 and 10. And then you get 6, 7, 8, and 9, which don't have any other multiples. It's just a number themselves. So you get basically a set of lists. So the interesting thing is then that you get this mathematical notation thingy. So between the square brackets is a reduction. So it's reducing a set of values to a single value. And it's using the thing between the brackets to do that. And that operator is, if you are mathy, you'll know that it's set theory. It's a symmetric set difference. And what does symmetric set difference mean? So suppose you have two different sets, a set A and a set B. The thing that is returned, if you get the symmetric set difference of those sets, are all the values in A that are not in B, plus all the values of B that are not in A. So make this concrete. List A of set A has the values 1 and 2. Set B has the values 2 and 3. Well, 1 is in set A and it isn't in set B, so it's included. 2 is in set A and it is in set B, so it isn't included. And 3 is only in set B and not in set A, so that's also included. So we get 1 and 3. Now, the trick is if you apply this to all of these sets with the numbers and their multiples, you get back just the primes, because the multiples will be in multiple sets. So it's a very unintuitive solution, I would say, unless you really know your set theory. But you can write this out and do it for a very small number. Try 8 or something like that. But you can write this out, and then you'll see. What you do have to remind is that you do this not on normally, if you do reduce, you take pairs of values, you reduce them, you get a new value, and then you do that with the next value. So you have this iterative process, but that wouldn't work here. So this symmetric set difference works on the entirety of all those sets, so at once. But write it out yourself, and you'll have a fun time seeing why that is. But this is doing a nice. I like the Python version working with sets, and the fact that you have special operations on sets that can be very beneficial if you want to reduce things to the values that you want. In this case, you get the primes. It's not entirely efficient because you get all these multiples and you get sets of them. So memory-wise, this isn't great, but it is very, very concise. And in the end, while you get a set, and the function wants you to return a list, so you do keys to convert to a list, and then you do sort, because that's what we had with Python 2. A set is in principle unordered, and we want the results to be ordered. So the sort and keys are the simplest versions, actually. So simplest bits of the code.
Nice. Very cool. Thanks
absolutely.
for explaining that, Erik. So the final one, which is feels a bit more sane, even though it's probably for a lot of people more complex to get their heads around, is an F# version. And this is recursive. Take us through this one, Erik.
This is like a mix between some of the things that we saw previously. So F# isn't a purely functional language, so you could actually implement the algorithm that we did in the other languages here too, where you just create a sieve once. But let's, for the sake of argument, just assume that we want to do a purely functional implementation. And that means that we can create our sieve. We're doing that in line 11. So you see between the square brackets 2 ... limit, range again. So all the numbers from 2 up until the limit. So we have a list of those numbers. But we can't cross off anything from that list, because that list is immutable. It will never change. So the thing that we need to do is we're going to have to create new lists. And that's what we're going to do within our sieve recursive helper. So the sieve function takes the candidates. So those are the numbers that could be primes. And then you have an accumulator, and those are the numbers that are primes. So you can sort of see like sieve is our sheet of paper with only the things on it that are that haven't yet been crossed off. It's almost like we're cutting out things of the paper. I don't know what the analogy would be. But we're making the paper a bit smaller and smaller.
With a big stick. Yeah.
Whatever the analogy is that works for you. Of course, this is recursion, so we have to stop somewhere. Of course, like with any list recursion, the easiest base case is usually the one where you stop when it's an empty list. So that's on line 6. We're saying if there are no candidates left to check anymore, we're done. So the thing that we return is all the primes that we found. We're doing list.ref, which means that the accumulator is reversed. And that's because in many functional languages, it is way more efficient to add something to the beginning of the list than to the end of the list. So that's also the case in F#. So we're going to see in a minute that we have been adding primes to the beginning of the list, which means that the last prime is actually the very first one in the list. So we need to reverse it. But we have other videos too if you are interested in knowing more about this. But the more interesting case is where we have a non-empty list of candidates, which means that the first element in that list is the prime, because otherwise it wouldn't have been in the candidates list. Then the rest is all the other elements. On line 8, we're creating a new list. And that is where it becomes slightly inefficient, like our previous solution. And this is giving us all of the multiples of that prime. And then to do the actual recursive call, at the end, we're doing prime : accumulator. So that's prepending the prime to the list. So basically, we're going to keep track of this prime too. We're going to add it to the list of primes we've already found. And then for the remainder of the candidates, which is like our failing paper analogy bit, we're saying all the rest except for the multiples, which actually reads quite well, I think.
It does.
But it is creating a new list again. So we have a list of candidates, we have a list of multiples, we're creating a new list of all the candidates except the multiples. So this is absolutely very, very inefficient, although there are tricks that under the hood can happen to make sure that the lists are less bad for your performance than they are, but it's still bad. And we're still, it is in the spirit of the Sieve algorithm, but it's not really the Sieve algorithm, I think.
Yeah. And this is using tail call recursion again, which we discussed in the recursion video, which you should go and watch if you haven't, which means that this will replace the previous stack, the previous frame on the stack, which will keep it a little bit more efficient. We're not keeping all of those lists in memory at once. We are sort of able to garbage collect the older lists, but it's still, as you said, it's not the true bit of paper with the crossing and the things. It's, copy and paste that list every single time, throw the old one in the bin. It's a little bit slower. But yeah, it's a nice solution again. It's another nice use of recursion. I think this, Erik, I think it's quite clear what's going on, especially when you talk it through like that. One nice thing as well in F# is the fact that you have to explicitly specify that this is a recursive function as well. That's a useful little bit of F#, I always think, that just makes sure that you know what you're getting yourself into, and it's a deliberate decision to call something recursively. Cool. Well, those are all our solutions then. I hope that was a fun little tour. It's definitely really interesting for me to look through that, to go through those with you, Erik, as well. I learnt lots and remembered lots and refreshed lots in that. So I hope it's been useful for everyone watching. As I said at the beginning, please do leave a comment. If you've enjoyed the video, please give it a thumbs up. That really helps us. And don't forget to subscribe if you would like to see more. And we'll see you in the next one of these videos. Thanks for watching.